In this video, I'll describe a new type of statistic called the F-statistic and how we can use it as part of the analysis of variance. In the last video, we looked at the research question of whether physical handicaps affect people's perceptions of employment qualifications, and stated a null hypothesis that the mean scores for each type of handicap would be the same. Then we looked at the ratio of the variation between the sample means to the variation within each group, as an intuitive way to see whether there was some difference between the population means. So let's look at a statistic that will formalize this. Now, one of the ways you've seen to measure variation is standard deviation. It turns out that if you have multiple samples, you can't add their standard deviations to get the standard deviation of the groups combined. However, if you square the standard deviation, you get something called variance, and you can add variances of samples together. So we'll use variance to measure the amount of variation. And in this computation, we'll write J to represent the number of groups we're combining, and we'll write N to represent the total number of observations. So in this particular scenario, J is 5 because we have 5 different groups, and N is 70 because we have 70 data points. So for the numerator, we want to find the variance. So we'd take the 5 sample means and compute the mean of those 5 values. And we'll write this as a y with 2 bars over it, the mean of means. Then we'd look at each individual mean, which we'll write as y bar sub j, and subtract, and then square this difference. And then we'd do this for each of the individual means and add all of this up. Then, since we're comparing j groups, we'll divide by j minus 1. So this is the variance between the means. And this numerator is usually called the sum of squares, and the denominator is usually called the degrees of freedom. Like in chi-square analysis, we usually think of the mean of means, y double bar, as fixed, which means that in this scenario, 4 of the group means can vary, but the 5th one is fixed, so there are 5 groups and 4 degrees of freedom. Next, for the denominator, we'll start by taking the sample mean for each group, which we'll write as y bar sub j, and then take the observed values in the group, which we'll write as y sub ij, and subtract. Then we'll square these differences and add them up within the group, and then add up these sums across all of the groups. Then we'll divide by, well, not quite n minus 1. There are a total of 70 observations, so there are 69 total degrees of freedom, but we already used j minus 1 of the degrees of freedom for the numerator, so we'll also subtract that j minus 1 from the n. This numerator is called the sum of squares for the error, to distinguish it from the sum of squares in the numerator, which is usually called the sum of squares for the treatment. And the denominator is called the degrees of freedom for the error, and the numerator is the degrees of freedom for the treatment. So now we have a new statistic that lets us measure the ratio of the variation between the sample means to the variation within each group. And this ratio is called the F-statistic. And for our particular data set, where we had 5 groups and 70 observations, if we computed the F-statistic, we'd get 2.86. Now, we'd need to see whether this statistic is large enough to provide strong evidence against the null hypothesis. So what we can do is to make a model that reflects our null hypothesis that the 5 population means are all equal to each other. The way we can do this is to take the data from our 5 samples and combine them into a single model. Then we'd set this to draw 5 scores at a time, 1 for each group, and repeat 14 times because we had 14 observations in each group. Then we'd simulate drawing 1 score for each group, and again, up to a total of 14 scores for each group. Then we'd compute the F-statistic using our formula. And then we could repeat this many times. Here we'll do it 1,000 times. And then we can look at the sampling distribution of these F-statistics. Here is a histogram of the sampling distribution of the 1,000 statistics we simulated based on the null hypothesis that all of the population means are equal. And if we had simulated 1,000,000 statistics, the graph would look like this. And then if we look at our observed F statistic of 2.86, we can compute the probability of getting our observed statistic or larger. And this probability, the p-value, is equal to 3.01%. This tells us that if the means were all equal and we took many samples of 70 scores with 14 per group, we would get an F statistic of 2.86 or larger in only 3.01 of these samples. Since this probability is relatively small, it is strong evidence against the null hypothesis. And the means are not all equal to each other. Now, this doesn't specifically tell us which means are significantly larger than which others, but it does tell us that, yes, visible physical handicaps do affect people's perceptions of employment qualifications. Now, most statistical software will automate this process of computing the p-value for you using a parametric model rather than a simulation-based model. A parametric model uses a formula based on something called a beta function to generate the sampling distribution of F statistics. Using this parametric model rather than simulation can be significantly faster because you don't have to set up the simulation. However, if you do this, there are 3 conditions that need to be met. First, each population has to follow a roughly normal distribution. Second, each population needs to have roughly the same variance as the others. And third, each of the observations in each group needs to be independent from each other. To check the first 2, you could make a graph of each sample to check the shape and variation to make sure it looks like a normal distribution and that they're all about the same width. For the third, you need to ensure that one observation doesn't affect any of the other observations in your study. Now, let's summarize what we've seen here. ANOVA, or analysis of variance, is a technique for making statistical inferences in situations when you have multiple populations and one quantitative variable. The null hypothesis is that all of the population means are equal. The F statistic is a single number that measures the ratio of the variation between the sample means to the variation within each group. We can compare the observed F statistic to a sampling distribution of F statistics based on a null model. And we can make this sampling distribution either through simulation methods or parametric methods. The former can take some work to set up, but using parametric methods requires that your data meet some particular criteria.